All right, well, it's a pleasure to have Sarah back and to tell us about more about group trisections. Oh, and next week, who's next week's Ty Lidman, right? Or no, is that?
Oh, cool.
Oh, wait, I may be wrong about that. Next week.
I did notice it was someone I recognized. But
No, Ian Zemke. Next week, Ian Zemke. So,
cool.
all right, go for it.
Start. Okay, so even though I'm kind of just continuing, it's probably good practice to do a little bit of a reminder. And also, I think this will be pretty short, so I think that's good. Like, I'm hoping this will probably end with lots of time before the job talk. So, yeah. Basically, just going to do some examples and talk about the algorithm that I kind of like worked up to last time. But the general setup is that like the original story is that there's this one-to-one correspondence between, well, there's this bijection between trisected four manifolds and group trisections, loosely speaking. And then the natural question was, well, we know that if we have a surface sitting inside a trisected manifold, four manifold, it inherits this bridge trisection from that trisection. And so can we do the same thing on the level of surfaces? And so going from topology to algebra is just applying Van Kampen's theorem to the various pieces. And I kind of talked about that decomposition last time. And then going this way is what we're trying to do in our project. And I'm going to actually talk about the algorithm that allows us to go that way this time. And so, here we go. This is just also to remind you of like what the pieces are of what we're doing. So here's our surface on the left, and then here's the cube on the right. So the surface is described by, first we have in S2, we have 2B points, and that's our first group is S2 minus the 2B points. And then we have three tangles, each sitting in a copy of the three ball. And so our next groups are these three balls minus these tangles. And then we put two of these pairs together to get unlinks in S3, and then we can cap that off with a disk in the four ball. And when you put all of those pieces together, then you get your surface in S4. So that's the idea. And those are all the various pieces.
Sarah, I feel like something, maybe, yeah, no, you had it there, right? The other thing to emphasize, just scroll up a tiny bit the other way, dip down, whatever, up, down, that way, is that that your third layer of groups, the three spheres minus the unknots, is the same as four balls minus discs. So it's kind of like which way you want to think of it doesn't matter. I used to worry about that.
Gotcha. Yeah. There's this kind of like this, in this level, there's like two steps that happen over here being joined into one. Yeah. Cool. And then, right, what do all of these groups look like? So this looks like a free group on two B minus one generators, but we're going to think of it as the free group on two B generators mod this relation. And then these second groups here that are the complements of tangles are going to look like a free group on B generators. And then these third groups are going to look like a free group on C generators, where C is the number of disks that you need to cap off these tangles. Okay. And so then I ended with this theorem, and I have this read because I want to make a note. I didn't want to forget that I missed something in the definition. So I guess let me start from the beginning. So let G be a group that is the fundamental group of a knotted surface, and fancy G is a given group trisection of G. And this is the definition of group trisection of G, but as Dave pointed out last time, like I should add and such that this whole cube pushes out to G. Because I was getting confused, because really, so the thing I want to highlight is like these three epimorphisms determine the whole cube. So that's like really the data of the group trisection, but the definition like should be, if you have a group trisection of a group G, then the cube should like push out so that G is your final group. And then we have this extra condition that the images of the generators of these three epimorphisms are conjugates of the generators in these free groups. And then there, if this is all true, then we can get a knotted surface with that group trisection. And this is really a work in progress, especially determining this. There's kind of like a uniqueness issue going on that we're trying to like, we think we have it, but we just have to like nail down the details. So that's where we left off. And so what I want to describe is how to actually get, if you start with these three epimorphisms, how do you actually get a tangle and then a surface? And really the hard part is getting the tangle. Once you have the tangle, everything works nicely and you get, once you have the three tangles, everything works nicely and you get the surface. So what I want to first do is, well, yeah, right. So let me write this down. So algorithm. So what I drew, the picture that I drew of the surface above was what's called a triplane diagram for the surface, but this algorithm is going to construct a shadow diagram instead, which is a different way of representing these surfaces. So I want to remind you what a shadow diagram is. But so this constructs a shadow diagram for a tangle from an epimorphism from pi1 of the complement of 2b points in S2, mapping to this free group on B generators. And so what is a shadow diagram for a tangle? So given a tangle T, that might have like different components. So that this tangle is all of them together, all of the components together. A membrane for a strand little t and big T. So this is just one of the connected components of your tangles, is a disk in B3 such that the disk only intersects the tangle at that one strand. And the boundary of the disk is the tangle union some other piece, where this other piece lies in the boundary of the three ball, is an embedded arc where its boundary equals the boundary of the tangle. And this is the type of thing that is much better seen with a picture than words. So let me draw a picture of what I mean by this. Oh, and this thing we call, this is called a shadow. And if it's not clear already, you'll see why in a second. So here's my tangle. So this is the boundary, and this is my 2B points, and my tangle is the following. Okay, give myself some room. Okay, so each of these, so there's two components, two strands of my tangle, and each of these has a membrane disk. And so let me just draw one of them. What color do I want? So let me do the tangle, the strand on the left. It would look something like this. So this disk is, you come around the back here, and then it wraps on over to the other side like this. So let me label my diagram. So this is T. The gray thing is delta, and let me actually color it in to really drive home the point. And so this disk only touches this one strand. And the boundary of this disk is that the tangle, this strand of the tangle here, union this part here where it meets the boundary. And this is the shadow. And so let me put this in like a different color. That's not bright enough. Let's do blue. And so this blue part here is the shadow. Some people like to say disk bottom because that's literally the bottom of the disk. Whichever imagery makes more sense to you is fine. And so then a shadow diagram is just a collection of all of these shadows for each of your disks. So a shadow diagram is a collection of all of these shadows. So for this example, I only drew one of them, but the other one, the other shadow would be something like this. And you can picture the disk. I won't draw it because it'll get too complicated, but the disk kind of follows this strand. So it kind of comes out like this. So the two disks are like swirled together a little bit. And so then for the diagram, we just kind of ignore the disks and we just draw what's happening on the sphere or whatever surface we have. And so for this example, it would look like that's for one of them and it's for the other. So it's maybe somehow, no, I won't say that. Yeah, so similar to a triplane diagram, but not the exact same thing. There are ways to go in between triplane diagrams and shadow diagrams, but won't talk about it here. But the shadow diagram is what we're going to get as the result of our algorithm. So any questions about what these are?
Maybe this is just a distraction, but is it important to say that the disks should all be disjoint, like a whole system of disks, or is it can you just sort of one disk at a time find its shadow and maybe to be safe, just say a system.
Yeah, I feel like they should be disjoint.
Yeah, so maybe a shadow diagram is a collection of shadows of a system of disjoint disks, perhaps.
Yeah.
Maybe you don't need to say that, or maybe in this genus zero case, you don't need to say that or something. I'm not sure.
Why not?
I mean, the only concern is them intersecting in their interiors.
Yeah.
And maybe in the four ball, that's not going to be interesting. But.
Yeah.
Once again there. What did you just say?
I was just saying, like the way what Sarah originally wrote, she was just sort of implying for each strand, you find a membrane and then you take its shadow, and then you do that to the next strand and you take its shadow, and then you remember all those shadows.
Right,
and
you have to do them all together, right?
You kind of seems like, to be safe, at least, you ought to take a system of membranes that are all disjoint from each other.
Otherwise,
yeah. For example, the shadows. Oh, here's a question: Can the shadows arcs cross each other? And probably don't.
They're not supposed to.
No,
right?
Yeah.
Right. Yeah. Okay.
So it's like when you draw. So this is just for one tangle, but then when you draw all three together, they can cross each other. But like for one tangle, they can't.
So you take a union of disjoint disks. I mean, that's what trivial tangle is supposed to have, right?
Yeah.
I mean, every arc by itself will, unless it's knotted, it's going to be right. So you want to,
Yeah. Thanks for the clarification, detail addition. I don't know. Yeah. Any other questions or comments?
So algorithmically, the thing that goes in front is supposed to go to the bottom, right? And if you're trying to look at a picture of a tangle and draw something algorithmically.
Yeah. Yes.
Do you have an algorithm or?
Yeah, I haven't explained it yet.
Okay, great.
Sorry. Okay.
Well, you're going to explain an algorithm to turn the group theory data into the shadow diagram. I
Oh,
think
yeah.
Coordinate
No, I'm not
asking
talking
for an
about how to.
algorithm to go back and forth in the shadow diagram, the tangle diagram.
Yeah.
That's probably annoying, but
Yeah, I wasn't planning on talking about it. Jeff has a nice picture of like you're looking kind of at what happens at each crossing and you're going one by one. I honestly just kind of do it by trial and error. It's like once you kind of like not too many different things can happen and you just know however many twists you have, that's however many times you're going around. And but yeah, there are ways, but I wasn't planning on talking about it.
Okay, cool.
Yeah. But yeah, it's exactly right. Like if you have your tangle laying up, you could, you're just taking these things and pushing them down into the surface. Yeah. Okay. So let's talk about the algorithm, and I'm going to talk about it by way of example. So here's an easy example. So I'm going to let my value of B be 2. So I have 4 bridge points, and I'm going to call this A. This is generated by A, B, C, and D, but mod the relation that A, B, C, actually I'll just write it out. A, B, C, D equals 1. And then this is mapping to a free group on 2 generators, which I'll call X and Y. And I'm just going to send my generators to the following things that, again, remember, need to be, these need to look like conjugates. So I'll make this X, Y, Y bar, X, Y, and then Y bar. Okay. So the setup is we draw our S2 as a line and put our points on the line. Our points to our bridge points. And then we'll imagine that our base point is like way off at infinity or something, like maybe up over here. And so we can describe each element of the fundamental group by just little half arcs going around each point. And so I'm going to erase this and just leave a half arc. So this is A, B, C, and D. And then from this surface relation and the map, we're going to figure out how to connect these points and get a diagram. So the surface relation tells us that A, B, C, and D equals 1. And what you do is you look at the image of each of these things, but you remember where they came from. So A maps to X, B maps to Y, C maps to Y bar, X bar, Y, and D maps to Y bar. And this equals 1. And what we do is we start to cancel, and every time you cancel, we draw an arc between the points that they came from. So first we could cancel this Y and Y bar, and this came from a B and a C. So I'll draw an arc between B and C. And then second, we could cancel this X and this X bar, and this came from A and C. So I'll draw an arc between A and C. And then last, we could cancel these guys, and this came from C and D. And so then we draw an arc between C and D. And so what will happen is at each point, you'll have like an odd number of things. And so if you just have one thing, then you just connect that to your endpoint. And then if you have a bunch of guys coming in, like we do in C, then the innermost one goes to your endpoint. And then this other strand, and now the colors aren't going to match up, 2 different color, goes around like that. And so that looks kind of weird, but we could clean it up a little bit. B, C, D. And so this becomes this shadow diagram. If we take this strand and then just move it to the other side. All right, any questions?
Yeah, how unique is this?
Yeah, so like, can you cancel in a different way and get a different thing? Yeah, so we're pretty sure the only thing that can happen, so yeah, we haven't written this out super precisely.
If you try to cancel it some other order.
So I think the only thing that can happen is if you have things that look like this showing up in different elements. And what ends up happening is that you can cancel in two ways, and one way will give you a fine shadow diagram, and the other way will give you like just like a weird closed component. And so you just pick the way that gives you the fine shadow diagram. And there's definitely like some weird details missing there, but that's like the general idea.
I see. So we don't even necessarily know this gives you a shadow diagram in general.
It should, if you have,
right.
If you have a map of this form, you can definitely get a shadow diagram. But if there is ambiguity to cancel, like if this thing does happen, then one way will give you a shadow diagram, one way will give you a shadow diagram with an extra component. And we did just meet today, and we think that the difference between whether there is this closed component or not comes from a handle slide. And I'm still digesting this, but I think Vince will talk about it more on Wednesday, or Thursday. So I don't know, maybe that's interesting.
But I think Gordon was asking, can you just, for this simple example, do a different order?
For this example, it'll be the same.
Oh, there isn't any other choice.
Yeah.
There is.
So like you could change the order, but the picture won't change.
The picture won't change, right?
Yeah, the only ambiguity comes from having things of this form. Yeah.
But how would that ever show up? After you canceled something already inside, and then that would show
up. Like what an example, like
I mean, it will not show up when you first look at it. It will show up only after you cancel something. Like if it was x bar y and y bar x bar.
Yeah. Right. Yeah. And I forget. I could look up an example, but I'm not sure if it would be super enlightening. But yeah, you would have to have some other stuff in there. Like you would have to have y's somewhere, but yeah, then once the y's go away, then you're left with something that looks like this, and then that's where the ambiguity comes in.
This must be some kind of previously studied combinatorial problem in this, right?
Yeah. There's a lot of things that we've come into it's like, how do free groups work and what? And it's like, surely somebody knows this, but yeah.
Yeah, I mean, people tried to prove Poincare conjecture, right, from canceling stuff, I think, a long time.
Oh, cool. I'll have to look. Yeah, I don't know if I know about that.
I mean, they didn't go anywhere.
Yeah, this could be cool to look into.
But people must have looked at this.
Yeah.
I mean, I remember Dave Galuski saying that, I mean, he was doing something with, trying to figure out things from, group presentation that give you pi 1 = 1 and stuff. And so he was playing with all kinds of things like that, a zillion years ago. People played with things like that.
Cool. Well, so for the rest, I just wanted to talk about a few examples, and I could explain. So I wasn't planning to talk about much of the proof of how our overall thing works, but once you get your 3 tangles, so kind of this algorithm is kind of like uniqueness, and then there's, existence, and then there's a uniqueness thing that's still a little weird, but we've kind of been working on it, and it uses Dane's lemma. But once you have these 3 tangles, everything is totally fine, because the union of the pairs of tangles are an unlink, and Kneser's theorem implies that the unlink is detected by the group of its complement. And so then once you have So then you get this unique trivial disk system, and then you get your surface. So totally getting these tangles is like the hardest part, and then everything else just follows really nicely, especially because of this theorem about the unlink being detected by its group. So I wanted to just show some examples, and that was pretty much all I wanted to talk about. So I put them both up here. So this was the first thing I wanted to show, and the purpose of showing you this example is not for you to understand what's happening at all, but just to show you what a more complicated result of this algorithm can look like, because the one I showed you was extremely not complicated at all. And so this is the tangle that I used. I think this is one of the tangles of the 5 twist spin of the 2-3 knot. And so there's like 5 twists going on here. And so it's super complicated relation with 8 pieces being mapped in, and, or 8, what I was saying, 8 elements, 8 images of elements canceling with one another. And so what you get once you do all of these cancellations is this following thing, where these numbers here, this 13, 22, and 15 mean that there's that many strands. So I didn't even draw it all. And I started to make it look like a shadow diagram, and gave up very quickly because I didn't want to do that many of them. So I actually don't even know if this is correct. This is supposed to be equal to this. And I just stopped. I said, it's believable that this is that. And then I kind of stopped. So that could be an exercise for the reader, but just an example of something that is a little bit more complicated. Yeah, so you can see, like, for each of these, like here I have like 13 strands coming in here, and then 22 coming in here. So whatever the middle strand is ends up going to X2. And then I have all these other strands that I have to like pull around. Yeah. And so then the last thing I wanted to show was this RP2 example, going both ways. I can't remember if I actually did talk about this at all last time. I think I might have. Now all of the talks are blurring together now, but I'll talk about what's going on anyway.
You only briefly mentioned it, I think.
Okay, yeah. So this is, in this picture, there's kind of a going both ways, from topology to algebra, and then the other way. So this is the from topology to algebra story. So this is a triplane diagram of RP2 and S4. And so each tangle here, oh no, don't do that. Gives you, oh, stop it. Okay. Each tangle gives you 2 relations. And so you get your first 3 groups are going to be free groups of rank 2. And then, yeah, I didn't really want to go through this because it's like not enlightening or interesting. But if you then combine, if you throw relations from pairs of those things together, then you get free groups of 1 generator. And then if you throw all of the relations together, what happens is they all get identified, and you get that the generator you're left with equals the inverse of its own inverse. And so this overall group is Z2. But here's the kind of the more interesting thing. If you start the other way around.
So Sarah,
yes.
Maybe I'm jumping ahead to what you're about to say, but when you say like X1 equals, the top, in the red top left, X1 equals X2 bar, X3 equals X4 bar, you're actually implicitly describing the map from free group on 4 generators mod relation to free group on 2 generators by saying that X1 maps to, say, A, and X2 bar maps to A, or something like that, right?
Yeah, so I'm kind of like abusing notation here and just using X's throughout, and then just showing how they're identified at each stage. Yeah, exactly. So really, like, right, so I call these things, it's exactly what you said. Yeah.
I see. So your free group on 2 generators is labeled X1, X3. I see. Yeah.
But I mean, yeah, and it probably would have been better if I called it
blue x1, x2, right? Okay, so those guys are not the same.
Yeah, color, right. I always forget I should I have conventions for when I do stuff and I forget that not everybody. Color is always very important in my notes, and if two things are different colors, they're usually not the same.
Right.
So these are all different generators. And then they become the same at the end. Yeah. Yeah, so right. So what happens? So yeah, you're right. So we start off with these 4 generators for each one. And then we see how they're related. And so this is these first 3 epimorphisms. So if we want to go the other way, then we take the surface group, and I realize I have it in a different order here. It's because there's a convention about orientation that doesn't matter. But this is
So
the
where
surface.
does now x3 and x4 bar come from in that first thing on the bottom?
X3 and X4 bar.
You have x4, x3, x2, x1,
Yeah.
and say it's x4, x4 bar.
Yeah, I'm about to explain that
Okay.
right now. So right. So this is a surface relation. And what I'm doing is I'm taking these relations from above. This is the map. And I'm plugging them in. I'm plugging them in here.
Oh,
So
you're
I'm
thinking
saying,
that it's true.
yeah. So X3 becomes X4 bar. And then I picked X1 to be X2 bar. And so that's where everything is sent. That's the image of the map. And so then when you cancel these 2 together. So you draw an arc from X1 to X2. And then you cancel these 2 together. So you draw an arc from X3. I'm sorry, I did it backwards. These 2 come from X1 and X2. So those give you this arc. And then these 2 come from X3 and X4. So that gives you this arc. And so then you repeat the same thing with each of these. So for B, I'm now making X3 becomes X2 bar, and X1 becomes X4 bar, and this gives you like the rainbow. And then this is the more interesting case because the map is a little bit more complicated because we have this crossing. So that gives you this conjugate in the image here. And this is why this conjugate condition is a natural condition, because that's what happens when you take the fundamental group of these tangles. Whenever you have crossings, you're picking up conjugates. And so what this means is that X2, the image of X2 is this conjugate. And so then we're going to end up with a situation that's actually pretty much identical to the example I did below. And I guess I didn't finish it, but the shadow diagram that you would get would be the same as the one I got below. And then if you pull up the strand, then you get the crossing that I have in my original picture. So that's kind of like a quick and dirty converting from shadow diagram to tangle diagram. But that's the shadow diagram that you get. And then if you picture pulling this up, then it becomes the same as your tangle diagram. And yeah, so that was pretty much everything that I wanted to say. Are there any other questions?
And the fact that you get unlinks comes from this condition that free group 1, that's what you get.
Yeah, exactly.
So that's sorry. Did you say that's Knaser as well?
The Knaser shows you that, what am I saying? Sorry, yes, it also, yeah, right. It comes from Knaser's theorem because the groups look like free groups. That means that we have an unlink in particular.
So a link component in S3 whose fundamental group of the complement is a free group implies the link is actually
an unlink.
An unlink. So that's the analog of what
I think
Rob
that's where you use
Poincaré
theory, the Poincaré conjecture, I think.
You said it does or doesn't?
No, I said I think that's like the analog of what you use the Poincaré conjecture for.
That's right, but you don't need the Poincaré conjecture here.
No, yeah, it's much easier.
Yeah. Well, I mean, that Knaser stuff is not easy, but
sure, yeah, okay, true.
They're both easy if you're willing to use other people's results.
Yeah, it's easy for me.
See, so what I was going to ask, but I think you've kind of sort of, I mean, you gave an algorithm to produce 3 tangles. And then what you would need to show is that when you put those 2 tangles together in pairs, you actually do get the particular push out as described. I mean, you get.
Well, you know, you get unlinks, right? Because
no, actually, just one first of all, when you just do this algorithm to produce one single tangle, you need to know that then you get a tangle. So therefore, you get a map from a free group on 2 B generators with one relation to a free group on B generators, and you need to know that's actually the map you wanted.
Well, that's how she constructs the tangle, right?
That's right. So it wasn't obvious to me from the original description of the algorithm that following this cancellation method is going to give you the same map on the groups. But now by example, I kind of see that, because that's exactly how you see that you get the group, is by seeing what cancels, right?
Yeah.
It's
kind of like proof by construction, but maybe not explained super explicitly well, but yeah.
But so
it's kind of exactly what you need to go the other way.
So this algorithmically, there is a uniqueness here, except for the choices of order, right?
Yeah.
So when you say a trisection, are you actually specifying the group trisection? Are you specifying generators and maps given by generators, or are you, because if that's what's specified, then that's totally algorithmic and unique, right? But
yeah, I think it cut out a little bit, but I think
specifying the generators, do you have there?
Yeah, I think that's like the exact uniqueness business that we're trying to kind of nail down. Like in the 4-dimensional paper, they use these like parameterizations, and you get this like bijection between like diffeomorphism classes of 4 manifolds versus group trisections up to like a stabilization operation and something, I guess
well, we thought it seemed kind of important when we wrote it to actually think about generators, not just abstract free groups. If that even makes any sense.
Yeah, well, that's what I was saying, is if you have a map given in terms of a presentation, right, of a map in terms of generators, then this is all algorithmic, right? If you just say you have a map, that means you have a freedom of choosing the generators, and then that's not sure.
And so I think it's like right now we're at a point where like there's different levels of like a statement that we could prove, and we're just not sure like how high up we want to or can go on that hierarchy. Yeah.
But because if you like fix the presentation of the group, so fix the generators, and then you have a map, then there is, except up to this little order of cancellation, then it's clearly unique algorithm.
Yeah.
So what was the situation in closed case, Dave?
Well, I mean, closed case, we thought of like, specific, each like a group trisection would be, there for each G, there is a fixed genus G surface group, which is a group with standard generators and standard relation. And then for each free group, that's a fixed group with generators and then maps between those. And then that whole setup gives a unique construction of a 4-manifold.
Right.
And then you can say, well, the other thing then you can say is, what does it mean for 2 group trisections to be isomorphic?
Right.
Which would be, you have one cube and you have another cube, and then you just have maps between all the vertices, going, so that everything commutes, isomorphisms between all the vertices of the cube.
Don't do generators to prescribed generators to prescribed generators. You just
actually, you don't even require, yeah, you don't require that. It's just,
you don't, because if you require that, then it's just relabeling, right?
That's right. So it's more than related, just any group isomorphisms that commute. So you have a cube to cube and commuting maps between them, then that induces a diffeomorphism between the associated trisected four manifolds. And so that's how a group trisection up to isomorphism determines a trisected four manifold up to diffeomorphism.
Up to diffeomorphism of the trisection.
Yes, up to diffeomorphism with the trisection, trisected object. We're up to trisected diffeomorphism, right?
And it's kind of because the compressing disks get mapped to not standard compressing disks, but some Handel-Slade compressing disks.
That's right, and you once again need Dane's lemma somewhere.
Yeah.
If I remember that right, I'm sure Dane's lemma comes up again at that point. You also need to know the fact that any isomorphism between two surface groups is actually induced by a diffeomorphism of the surfaces.
Right.
That's also a cool fact, and that's because, I mean, if it's the same surface, then it's, you know, the fact that the outer automorphisms,
cut it up on alphas and get a puncture disk and whatnot. So.
Pi1 knows everything about the mapping class group of the surface. And then the stabilization is kind of, that just comes for free afterwards. Once you know trisected objects are, determined, either the groups or the bijection between trisected groups and trisected four manifolds, then there's a stabilization operation on four manifolds. You just translate into stabilization on groups, and kind of just, there's no extra work to. So you just sort of pull back the up to stabilization statement on the four manifold, just sort of pull that back to the groups. Other questions for Sarah?
Did you think about my branch cover question?
I didn't. I told Ben and Vince about it, and then we haven't really thought about it yet. But
what's the branch cover question?
If you want to describe group trisections of the branch cover four manifold in terms of the group bridge trisection of this knotted surface. So it's I think
so you can get a trisection, right? So I see. But you're asking about just not. So there is a process to get the trisection, right, of the branch cover.
Right.
And saying so that when you're getting the trisection. Yeah.
Right. I think if you have a knotted surface in a four manifold in S4, then branch cover is described by some map from.
There is a bunch of us. This full disclosure, there is a bunch of us, including Ben, that started working on that trisection thing on the branch covers of branch covers of surfaces in S4. So
this was your winter trisection.
This was our winter trisection group, and we keep running. So I was interested in what you were saying. But we didn't try to think about it from the trisection, from the trisection, group trisection point of
view. Yes, I mean, my intuition was that it should be pretty straightforward to go from a group like Sarah's talking, like group picture right now, like Sarah's talking to a group trisection of the branch cover. And then another question I thought of was going the opposite direction, that if you
right. So what you have a easy thing to do is to go to the trisection of the cover, right?
right.
That's but then like a trisection diagram of the cover. But then if you have a trisection diagram of the cover, you have a group trisection right away?
Well, my intuition is that the dictionary between group trisections and trisections of surfaces in bridge position is not going to be so straightforward in other manifolds or other trisections. That
Yeah.
there be some extra subtlety when you're not working in S4 in genus 0.
Yeah, no. I mean, you don't. Right.
You can definitely go from the trisected surface to the group. That's just by one, like Sarah's saying.
Right.
So in principle, what Peter's asking for, you could just draw the diagram and then
Right, and then just
apply pi one. But you're really saying,
right, because
really
diagram you get, right?
Yeah.
The diagram for the branch cover you will get, and so then if you just apply the pi one to the diagram, the pi one, because you are given a diagram, you're also given a group trisection, right?
But my point is that you don't even need to draw diagrams, because the branch cover is determined by a map from pi one of the complement to SN or something. And then just by drawing some like arrows and homomorphisms, you should be able to,
to calculate the pi one of the branch cover. Yeah.
It's just sort of, you have some push out cube or whatever that is describing your group trisection, and like it should all be immediate without having to draw any pictures whatsoever.
It probably is, yeah.
Shall we thank Sarah and call it a day? Unmute. Awesome. Thank you, Sarah. I'm going to stop recording. Yeah.